welcome to the Nobel series. It's the third series now that we've done on the Nobel Prizes. And there is a trend. If you think back, for some of you that were here for the first and second ones, you'll recognize certain trends. And I want to say something about the Nobel Prize itself early on. But I'll tell you, this year, of the 3 years, if this were a wine, this is a very good vintage. This is a great year, especially the physics prize, with which most of you are pretty much familiar because of the previous series. But the chemistry prize, because of gene editing, because it's so important. It's probably the most important subject in science, in my mind, in the decade. So, next week is going to be very important and I think quite interesting and provocative. Now, the material this week is very similar to what you heard during the physics series, so I'm going to take some liberties. And some of the visuals, well, most of the visuals will be very similar. But that first one that you see there, that's the Milky Way. And as I pointed out, that bright spot or very shiny spot in the middle is a very dense cluster of stars. And it's where Sagittarius A is, or this giant mega black hole exists, which is what the Nobel Prize in Physics was essentially given for. Work on the genesis of black holes and confirming the presence of a giant black hole at the center of our Milky Way. So that's where it is. Now I got caught again with this thing. Yeah. There we are. So, but I'm going to swerve off a little bit because, oh, now my sound is off. Oh, I've been muted. There are lots of people who would like to mute me. Am I on? I think we're good. Yeah. Okay. I'm going to wander off to say that some of you will remember that last year's Nobel Prize in physics involved two things: the evolution of the early universe, but it also rewarded people who've done work on exoplanets or planets where there might be life. And it's very interesting to me that I mean, I follow this literature fairly closely, and it's exploded as I thought it might, because it would seem that there are several 100 billion planets within the Milky Way that could sustain life. I mean, just a year ago, or at least at the time of that Nobel Prize, we were talking about 4,000. So this is the kind of the current projection. Now, if you imagine, just do the math for a universe with at least 1 trillion Milky Ways in it, it's certain, it's as close to a certainty as possible that life exists elsewhere and probably in multiple places at different stages. And remember that I've used this analogy before, but if you were an alien set to explore Earth by chance, for most of our time here, or at least most of the time the Earth has been around, all life was single cells and not very complex single cells. So unless they were really lucky to kind of visit around now or within the last several million years, they wouldn't have spotted smart primates around. So then what are the chances that if life existed elsewhere, us finding them or discovering them and finding, and with serendipity, actually find complex life like our own, not the same as, but like our own, perhaps with a similar intelligence. I think that's a really interesting thing. And And I put up the next one because every session we had on the physics one, I included some of our ancestors, the Australopiths or Homo erectus or various other examples, and eventually modern humans beginning, say, 200 or 300,000 years ago. And no surprise, they were wanderers. And this is a kind of a map in progress. Last year's map drawn in a review article in Nature with times dating in it. And you can see already it's wrong, because if you look at that black arrow there in Southeast Europe, and it says 40, what's this? Something about this. Oh, somebody's coming in. Okay. But we now know that modern humans existed in that area probably 100, 110, 120,000 years ago. So this map of migration of our ancestors is a work in progress. But you can see how it moves across Eurasia and into the eventually Australia, and then eventually North America, maybe 25,000 years ago. So we were migrants. We were migrants within Africa. We were migrants outside of Africa. So and they didn't know anything about the subject that we're talking about. Nobel Prizes didn't exist. Nobel didn't exist. So that's a little bit of perspective to think about when we think about art and we think about imagination and creation stories, that there must have been millions of creation stories, narratives, myths over time that modern humans have been around. And if you think about science, it's another creation story, isn't it? It uses different tools, but it's another creation story, and very much a work in progress, like the others. So we'll move along, and lest we get too swollen ahead as modern humans, here's that cave art that I've alluded to before by Neanderthals well over 60,000 years ago. This happens to be a Spanish cave. So our close cousins were creating art, and if art, well, they must have had the imagination. They probably had symbolic language in some form. So that should shape our perspective of our own life, I think. It certainly does mine. And and here's another one that's interesting, because these are stone tools created by I would say 500,000 or 600,000 years ago, so before so-called modern humans. But you can really be waylaid over this, because think about New Guinea. New Guinea, up until say the 1910s, 20s, Westerners hardly penetrated it. I mean, it's an impenetrable large landmass of deep valleys and ridges and heavy jungle. And the early Westerners to see it, that's what they ran into. These were Stone Age peoples. And within 2, 3, 4, 5 generations, they were airline pilots. They had university degrees. So it shows that just because you found stones, and that was the level of the technology that they seemingly had, that the brain was capable of a lot more. And they probably used that good brain, or needed that good brain, to navigate the land in which they lived, something that we don't have to do. Or my head disappearing. All right. Okay. So I've just put in those things because they add a little perspective, at least they do for me. Now, what about Nobel? I'm not going to give the whole spiel on the history of the Nobel Prize, but I haven't said anything about it for the last 2 years. So he was born in Stockholm, Sweden, died in San Remo in Italy, interestingly enough, of an intracerebral hemorrhage, the same thing that killed Franklin Roosevelt. He came from a long line of creative, inventive people. And for the 16th, 17th century, Sweden was was a power, believe it or not, in Europe. And but for much of his life, the formative period in his life was in Russia, St. Petersburg. And his library reflected his broad interests. He wrote plays, he wrote poems. He was an interesting duck. 355 patents. And he established his first the first international holding company in the world, the Nobel Dynamite Trust Company. Isn't that an interesting one for the Nobel Prizes, or at least where the money came from? Well, what prompted him to be so generous? Well, we don't know, but it's interesting that 8 years before he died, there was an obituary. We don't know who put the obituary in the paper, but it was entitled "The Merchant of Death is Dead." So 8 years before he died. So maybe this preyed on his mind. I don't know. But anyway, his last will was set out in 1895, a year before he died, and he was certainly generous because 95% of his money went into the Nobel Foundation. And by today's standards, that would be about 300 million pounds. So that's a lot of money to continue with the prize. I noticed that every year, the amount that's given, I think it's 1.1 million if you get the whole prize. So not bad. That's US dollars. So I don't, and then look at the bottom here. He specified that his fortune was to be used to create prizes for those who confer the greatest benefit on mankind in physics, chemistry, and physiology or medicine, literature, and peace. No economics prize. The economics prize, in my judgment, is the weakest of them all. And it came in later, and it certainly isn't science, or it's not much science in my view. But we'll hear more about that later. Now, I love these orienting pieces because Lawrence Krauss, as you know, I've quoted him before, but this is a nice one of these perspective pieces. It says, one of the most poetic facts I know about the universe is that every atom in your body was once inside a star that exploded. Moreover, the atoms in your left hand probably came from a different star than did those in your right hand. And we are all literally star children, and our bodies are made of stardust. Well, I kind of like the idea that we're made of stardust. I hope you do too. It's but certainly those supernova were important for the creation of complexity in elements, right? And that includes the elements of life, but the heavier ones as well. So, well, here they are, Andrea Ghez, Roger Penrose, and Reinhard Genzel. Those are the Nobel laureates in physics this year. I don't know who does this. Well, I do know who does this artwork for them, but it's not exactly, they're not the most flattering of pictures, I think. But, and next week is worse. Anyway, there they are. And Roger Penrose, 89, he got half the prize, and then the other half was divided between the other two, Andrea and Reinhard, who essentially did the same kind of study. And I think what the Nobel Institute recognized was that they confirmed one another. The findings of both of them complemented one another and therefore made the case stronger. So now, this is in the Nobel Institute's own language, why they gave them the Nobel Prize. So for Roger Penrose, for the discovery that black hole formation is a robust prediction of the general theory of relativity, meaning we talked about Einstein's general theory of relativity, and one of the predictions he didn't make, but others did, looking at his equations, that a black hole formation would be an outcome for general relativity. So he confirmed that. and Andrea Ghez and Reinhard Genzel for the discovery of, and you know, the language of the Nobel Committee is important here. They don't say for the discovery of a black hole, because we haven't seen the black hole yet. Not this one. So look at what they say: for the discovery of a supermassive compact object at the center of our galaxy. Well, what else could it be? But they've chosen not to say it. And they also chose not to give this Nobel Prize until a black hole was actually seen last year. That's why Stephen Hawking lost out. Because he and Penrose were actually colleagues sometimes and friends. Now, what was Penrose? What did he bring to the table? Well, we're going to talk about this in a little more detail later. But Penrose, he's an interesting character. But he's a mathematician. He's a superb mathematician and theoretical physicist. Much better mathematician than Einstein, and very creative and gamey about his work. I mean, he enjoys playing with math, and so we'll see how that actually worked out for him. Now, what about the other two? And here's the point that I was making or made earlier. Each led a group of astronomers who are focused on the center of the Milky Way. Remember the first slide, that bright cluster of stars where this presumed black hole exists. And by the way, just to remind you, not just the Milky Way, but probably most, if not all, galaxies have a gigantic black hole at their center. And those black holes have a role. They're not just sitting there. They play a role in shaping the galaxy. So, but this is a prize, except for Penrose, given for what I call big science. I mean, this is a 30-year project, 3 decades, involving 2 major groups, from Max Planck and the other one in California. And so a lot of astronomers, a lot of physicists, a lot of engineers, a lot of time, a lot of building incredible devices and ones to kind of get around all the kind of the debris and artifacts that are created by our atmosphere. So it was 30 years in the coming for sure. This mass is enormous. I mean, 4 million solar masses, or 4 million times the mass of our sun. So very, very large. So this brings us back to the consequences of general relativity. Now, you know all this because you heard it in the last 2 or 3 weeks. But the general consequence of general relativity is that and you know this from that 1900 to 1930 series, it upended all previous concepts of space and time, meaning the Newtonian universe, where time was the same everywhere, to one where time was relative. And it was shaped by mass and fields. So an entirely new understanding of gravity and the basis for all the subsequent studies of the universe. So pretty important. All of this are just kind of checkpoints because you know it from the last 2 or 3 talks, but what are the consequences of general relativity? Well, one, the universe was expanding. Now, it wasn't, as I said in the earlier series, it wasn't Einstein who really cottoned onto it. In fact, he wasn't very happy with this implication. But the fact of the matter is his equations do predict an expanding universe. They also predict that masses will bend anything in the electromagnetic spectrum, including light. So light will be bent. and also if there's any kind of large event, like the collision of two black holes or neutron stars, that will create ripples in space-time, so-called gravitational waves. And the Nobel Prize was given 2 years ago, the first of the series that we did, for the detection of those gravitational waves. So I'm just going to skip past that. The other one, the obvious linkage of space and time. Now, an important one here of these three is that gravitational fields are associated not just with massive stars, but with dark matter, whatever dark matter is, and masses of stars, so groups of stars, galaxies, and the remnants of stars. So when these stars explode, which is the natural end, the kind of medium and large-sized stars, they leave a dense entity at the end of it. And if that's large enough, that can create a black hole by warping space-time around themselves. So now, to get to the point of this Nobel Prize, and I've said this before too, gravity governs the orbits of planets about the sun and the sun in its path around the Milky Way. It plays the key role in the birth of new stars from those interstellar clouds. It shapes space and time, we've already said that, and the rest of it we've already said. Now, this is my lovely, I'm not showing you that equation again, but I like John Wheeler's summary of relativity. Matter tells space-time how to curve, and curved space tells matter how to move. Perfect summary, love it. And this was one of these kind of wonky creations of artists. But what it does attempt to show, I mean, don't go into this in too much detail because the model fails, but it really does show a distortion in the field, in the space-time continuum, in this case created by Earth. So, and the sun a much larger one. Now, I've showed this slide before, but I think there are 3 points that I should have made stronger. Anyway, this is gravitational lensing. So in other words, if there is a star out of sight, blocked by our sun, so we can't see it, is there any chance that the light from that star might be bent enough by the mass of the sun to be in focus or converge on Earth? Well, yes, there is that possibility. And the bending of light around the sun was shown, as you may remember, by Eddington and his group in 1919, which created Einstein's celebrity, right? Because Einstein predicted that with an eclipse of the sun, he could show, or he actually predicted the fraction of the degree of the bending of the light that was curving around the sun to reach Earth, and he was absolutely bang on. So that got headlines around the world, and he was probably the first physicist to have celebrity status, and that was because of that. Anyway, but the point of this slide is see the massive object in the middle of it, but which could be a star or it could be a collection of stars. But the important thing is it's surrounded by a gravitational field, meaning that large masses create a field of influence, if you like, around them, and therefore, in this case, can shape space and time, and certainly bend the light. So I think that's that's really important. And also to realize that it's not just light that's being bent. Light is just one narrow set of bandwidths in the whole electromagnetic spectrum. So that anything I've said about bending light applies to the whole electromagnetic spectrum. So that's important to understand. Now, there is a history of this, and I went through this, I think, a couple of weeks ago, but it's amazing to me that such a prediction with so little evidence, but good reasoning would have come out. I mean, here were two men in the 18th century who independently reasoned that heavenly bodies, if they were dense enough, large enough mass, they would be invisible. And not even light would be fast enough to escape their gravity. So this is really a foretelling of black holes, isn't it? It's interesting. And then there's this interesting fellow, this German mathematician. It's an interesting thing because he was a very good mathematician, and again, better than Einstein. And he read, I mean, the publication of the theory of general relativity, I think, came out in January of 1916, and he read it while he was serving in the German army in Russia, and he did some calculations on it, and he came up with this idea that, look, gee, if the mass was large enough, it might so distort the space-time around it that the space-time would actually fold around that very dense object and form what we would call a black hole. But it has to be very dense. How dense? Well, if you compress the Earth's mass, that would be, if you compress that into something less than an inch in diameter, that's a lot of compression. So, and a very dense object. So black holes range in size. Those black holes, the one that we're going to talk, the Sagittarius A that we're going to talk about later this afternoon, the one at the center of the Milky Way, is one of these supermassive ones, meaning in its case 5 billion solar masses, but there are ones that are apparently billions of solar masses, maybe even more. Intermediate ones, when that work was done in 2015 on gravitational waves, that was caused by the collision of two black holes around between 20 and 30 solar masses in size. So they would have been intermediate. And small ones, and people argue about whether even tiny ones, quantum size, exist. Here's the one that gave the Nobel Committee the permission to award this Nobel Prize, because here is, despite Penrose and Hawking spending so much time talking about black holes and theoretical concepts, I mean, the missing link was a visual. You actually see a black hole. Well, here's the black hole. And it was, and if you're wondering why it's so fuzzy, well, it's so fuzzy because it was so far away. They were lucky to even see this. And, but there's the dark hole in the middle, and that corona of visible light, as we see it here, is really created by radiation, kind of whirling around, sometimes at great speed around the black hole. And so there was the evidence that gave the Nobel Committee that permission. Now, getting back to Penrose's, because when one of the questions here was, well, how does all of this, how does all this mass and energy become compressed or trapped, if you like, in a small spot in space? How does that concentration work? I mean, why doesn't the stuff bleed out or hemorrhage out? And he imagined mathematically that there could be complex surfaces. Think of the diamonds with different facets on them, different shapes. But the point is that all facets lead to Rome, meaning the singularity. All light and energy is reflected into the black hole. That's what his equations showed. That's what they demonstrated. That's why he got this Nobel Prize. And because of the mathematical basis for this hypothesis that there was a trapping of all energy and mass in the black hole. There are some, well, we'll deal with this in a second, but you know, when somebody says a singularity's density is infinite, I mean, most physicists and certainly mathematicians worry about anything like infinity. What's that actually mean? And so I'm not sure that, and this is one of the figures from the Nobel Prize award to Penrose. It's a highly simplified model, but what he's implying here is that light and space are transformed when they cross that event horizon, and they become fixed on or directed at this singularity, this one tiny, infinitely small spot. You can imagine the density. Well, the truth of the matter is we don't know what's going on in that black hole, but I'll just say a little bit more about this. We don't know what's going on in the black hole, but remember, he got the Nobel Prize partly because he showed that the creation of black holes was a prediction of general relativity. But beyond the event horizon, general relativity breaks down. It just doesn't work. And that's where quantum mechanics comes in, or at least we think it does. So this is one of these thresholds between general relativity, classical physics, if you like, and the new physics, or quantum mechanics, as you're now familiar with, from kind of the 1910 through into the 1950s, 60s. So two different worlds, two different visions of how the universe writ large and small work, but there seems to be a border between the two, and they don't seem to talk to one another, except perhaps in black holes or in the moment of creation in the Big Bang. Those are the two events where those two worlds, ways of looking at the universe really come together. But I don't think, well, I know that no one knows what's going on in the middle of a black hole. By the way, on that, there are three essays that you can download, and one of them is on black holes, and it deals with a speculation about, well, what is going on those black holes. Yeah. So now, we're on to the other two authors here, and just a kind of a roadmap to the Milky Way. It's not all galaxies are spirals, but most of them are, and it shows that that we're kind of on one spiral arm of the Milky Way, and there's that, and it's a long that giant black hole is 26,000 light years away. 26,000 light years away. I mean, that's an extraordinary distance. So all of this research that you're hearing about, that or at least half of it this year, is about stuff that is happening 26,000 light years away. It's amazing to me. Put another way, you're not going to get there in your lifetime going at light speed. So a long way away. So there's Sagittarius A. Now, what was the evidence? You know, all of this, these studies that were going on for 3 decades. What were they looking for? Well, they had one major hurdle, and that is that this large dense mass, or whatever it was that was at the center of the Milky Way, was I mean, there's a lot of stardust around, a lot of gas, very hard to see through, and then our own atmosphere. So those are all technical issues, which some very clever engineers managed to solve for them. But what was the effect that they were looking for? What would show that there was something really dense there? Well, as I told you about 10 slides before, surrounding a mass is a field. And that field exerts its influence on anything in that field. So if there are stars going by, it can change the trajectory of those stars and change their velocities. So they've been busily watching a small number of very bright stars over about 15 to 20 years and tracking them and seeing if their trajectories are changing in a way that would suggest that there is some horrendous field there, gravitational field, driving the trajectory. Okay, so that's the key. And Reinhard Genzel, just at the bottom of the slide, says that the observational breakthrough, and that was that these stars precessed, meaning these ones that are in the field and being influenced by that hugely dense mass at the center of the Milky Way, causes those orbits to change each time round. They precess. And that's the evidence for this large mass. And then he says at the bottom here, this observational breakthrough strengthens the evidence that Sagittarius A must be a supermassive black hole, 4 to 5 billion times the mass of the sun. Well, that's what he said. He's also the director of the Max Planck Institute, so I forgot to mention that. And this is really language from one of the scientists involved here, but it not only do these stars change their orbits because of this large dense mass, but also some of them speed up to incredible velocities, maybe 0.1 of the speed of light. That's pretty fast. That's really fast, and that's an effect of this large mass on the trajectory and the speed of, in this case, this what's called S2. Now, I mentioned the challenges of the Earth's atmosphere the last time. I mean, the atmosphere is about 100 kilometers thick. And I think one of the biggest problems they've had over the years is that the temperature in the atmosphere varies a lot. And sometimes there are kind of hot spots or relatively hot spots and relative cool spots relative to the atmosphere surrounding them. And those differences create a lens-like effect and distort images. So they had to kind of, that's where the engineers come in. By the way, all of these major projects, gravitational waves, this project being celebrated and awarded this year, they really depend on engineers. I mean, if it were left just to the physicists, this stuff wouldn't happen, and we wouldn't have satellites up there, and magical telescopes doing all kinds of interesting things. So, so I just wanted to inject that. Now, some things that we don't know. And I've already alluded to this. In the black hole, the general relativity breaks down at the event horizon. So one of the things is that's very current in physics, astrophysics, is this business of, well, what is the nature of gravity? Well, we thought Einstein had kind of solved that with general relativity, and it certainly works at that level. But it obviously doesn't work with black holes, at least in the interior of black holes. So then the question has come up, well, gee, maybe we should rethink gravity. Maybe gravity should be thought of as granular, as having particles, and they've even been given a name, gravitons. And that there's such a thing as quantum gravity. I haven't a clue, and I just read a very dense, almost incomprehensible article from MIT a week ago on this. So I'm no better off, except my conclusion that I don't think they're much further ahead, except they're maybe brighter and certainly much better in the math. So now, one of these things that comes up is imaginary thing. What would happen if you jumped into a black hole? Well, you know, if you read Stephen Hawking's book, and anyone who writes about black holes, they talk about information. Information, meaning that information about you, about how you were structured, the atoms that comprise you, I suppose even psychologically, who you are, the nature of you. That's all information about you, but there's information about all kinds of things. So what happens to that information when it goes through the event horizon into the black hole? Is it forever crushed into bits and pieces and beyond redemption and reconstruction? Well, it's interesting. Several theoretical physicists think that it's possible when black holes break down, and they do leak, and eventually they kind of peter out, that information theoretically might be reconstructed. It's a totally crazy idea to me, but theoretical physicists are great on such ideas, and I credit them for it, because we wouldn't be where we are without them. But I'm not sure I buy that one. But the other intriguing possibility, of course, is that, or the theoretical claim is that when at the singularity time, there is no time. It doesn't just stop, there is no time. Remember that the same thinking went into the Big Bang. At the very, very beginning of the Big Bang, there was no time. There was no before time, there was no time. And remember when we talked about quantum mechanics and quantum physicists claiming that at that level, there is no time. No past time, no present time, no forward time. Wow, isn't that interesting? And also, that if and I've said that in this talk, if the mass is dense enough, then time slows and eventually stops, just like my voice is now. So time stops. It's hard to get used to that kind of thinking, isn't it? Because we live in a world where we have watches, and we safely predict that if our watches are all synced, if I look at the clock on the wall, it'll be the same as here. Or if I'm in an airplane, it'll be the same as it is on the ground, or on the ground as it is on a mountain. But it is not. It is demonstrably not. So time is variable. So maybe time does stop. And of course, one of the jokes, the things that Stephen Hawking was often asked, well, can we go back in time? Is it theoretically possible to go back in time? Or is it possible to go forward? And I think I think he would say that yes, you can go back, but not forward. There is a directionality to time. So anyway, well, we won't. So I'm just going to close on this one thing, because I think I read this to you, because I love these things that set perspective here. So this is again Michael Shermer. So what science tells us, which is what the physics series is all about, and half of this series, what science tells us is that we are but one of hundreds of millions of species that evolved over the course of 4 billion years on a tiny planet among many, orbiting an ordinary star, itself one of possibly billions of solar systems in an ordinary galaxy, that's the Milky Way, that contains hundreds of billions of stars, itself located in a cluster of galaxies, not so different from trillions of other galaxies in an expanding universe that is very possibly only one of a near infinite number of universes. So there's the bookends for today, because it started out, remember, with is there life elsewhere? Is there a possibility of life? Yes, just on the numbers, absolutely. And here we have this kind of gigantic perspective, and then thinking in the middle ground about that slide that showed the migration patterns of modern humans out of within Africa, out of Africa, around the Earth, and all of them wondering about stuff, just as we are wondering about stuff, and understanding only in part so far. So next week was a good one, a very worthy one. But next week is the game changer, is the biological game changer. It's a big one. So that's about gene editing, and it's not often that the original work, the seed of the idea, is less than 10 years old to Nobel Prize. Trust me, it's not often. And that's what next week is all about. So welcome to next week.